Before I start, I show you a video that I should have showed the first lecture, but I couldn't send it. So this is just, so I mentioned that you can find on YouTube many interesting videos about Starling murmurations, as they're called, or Starling flocks. And this is a very large group. I believe this is in the UK, maybe it's in Scotland, I'm not sure. But this is a very, very large group of starlings, as you can see. And it's very interesting to see how they move and how they turn very coordinated, in a very coordinated fashion, and they make these, these figures in the air. So it's not, you see what they just did. It's not exactly clear why. Perhaps someone spotted a predator or something, so they wanted to change direction, and this propagates along the flock, and it propagates quite fast. In fact, I don't have time to talk about this, but we studied the propagation of the information of the turn, and it turns out that it is wave-like propagation. And to explain that, you need to introduce inertia, something I will talk a little bit about today. Inertia, you need an inertial model. Unlike the Viction model, which has no inertia, you need an inertial model. And it turns out that you can describe this with a theory that's more or less like what you use to explain waves of order parameters in condensed matter system. So waves of order parameters are called second sound. Okay, that's wave. So this is kind of second sound waves, because there's not the density that's propagating. They're not density waves, although there can be density waves, but it's the order parameter, is velocity, the direction that's propagating. Okay, so that's kind of second sound. So these guys go on and on doing this. And in the end, eventually, they just find a place they want to go to sleep, and they just go to sleep. But for some reason, they do this for quite a while, right? Instead of just going directly to bed, they go around. It's like little kids. They don't want to go to bed. They just go around the house a little bit. I don't know. Okay, so now for the last lecture. Okay. So what so yesterday we talked about correlations functions. So now I'm going back to the experiments and midges and try to, so using all the things we learned about correlation functions yesterday, apply them to midges. Again, this is interesting because of the problem, but you can also look at this as a case study on how you apply these tools of statistical mechanics to a biological problem. And I'll try to go slowly and explain the reasoning behind the reasoning that leads to the results and to our conclusions. Okay. So the first observation is that swarms are not ordered. Okay. So I mentioned this, but again, you have the velocity. This is the polarization order parameter. So other kinds of order were tested. So it was tested where the swarm is rotating as a whole. It was tested where the swarm is expanding or contracting as a whole. And none of these order parameters give anything. You always get fluctuations around zero. Okay, so that's the histogram. Okay, the gray thing is what you expect from a completely random model. And so there's nothing going on apparently as far as order is concerned. But we learned yesterday that there's more to the system than simply the average. We can look at fluctuations. And fluctuations are not trivial. So if you compute the correlation function, this is the velocity correlation function. So this is we're doing a scalar multiplication of two vectors. The modulus of the vector are more or less the same. They don't fluctuate that much. So mainly this is telling us something about the orientation correlations. So the 3 columns correspond, these 3 columns are 3 different swarms of 3 different species. Okay, so midges are actually, it's a very loose term. These are 3 species that belong to 2 different families within the order Diptera. Okay, so they're insects, but then the 3 species do more or less the same. So the first row, this is the correlation function. Okay. The second row is the integral of the numerator of the correlation function, okay, which is related to the susceptibility. And the last row is the maximum of this Q, okay, for different swarms, okay. So what you see here is that the correlations are not trivial in the sense that they decay in the distance that, as you see, is much larger. Here, the dashed line there is the interparticle distance. That's how far apart they are from each other, these guys. So the correlations do decay, but decay in distances much larger than the interparticle distance. Okay, so they're not completely trivial. And the other thing that happens is that this susceptibility, it's non-negligible, okay? So let me briefly recall, so susceptibility, what does it mean is how it's a measure of how the system responds to an external field. So this quantity is computed assuming that you can apply a field that you can orient to set the orientations of the insects. So if you can do that, you can work out, you assume just linear response theory, you can work out that the susceptibility, which is how sensitive the system is to this field that's orienting the field, susceptibility is related to correlation function, okay? So even if that result, the precise details of the results, what is the precise relation of the susceptibility and the correlation function, you can write that strictly for small perturbations in equilibrium systems. But the general idea is valid beyond that, because the general idea is that is the Onsager principle, which you may have heard about, which is physically it means that if you pull the system out of the equilibrium, away from the average, it will try to go back. And it doesn't matter whether you pull it away force it away with a field, or whether it goes away from that average through spontaneous fluctuation. Once it's there and it's released, it will go back. And it will go back in the same way. Okay? So that's basically the idea behind the Onsager principle. And that's the reason why fluctuations and response are connected. Okay? As I say, if you are out of equilibrium, the details can vary. But the principle, the general principle is still there. So once you, the correlations here look non-trivial, okay? The susceptibility, as I showed it, is a number, so it's hard to tell whether it's high or low, but the susceptibility has a very interesting trend that gets you thinking. So the trend is this. This is the susceptibility plotted against the density. Actually, this is the interparticle distance. It's sort of the inverse of the density, okay? So the smaller, shorter the interparticle distance, the larger the density, and the interparticle distance is normalized by the size of the midges, of the insects, so that you can compare different species, okay? So all flocks or swarms are plotted there, and you see that you have that kind of power law between susceptibility and this interparticle distance or density, okay? And if you studied second-order transition, this reminds you of this sort of law. So we know that when the system is nearing the northern transition, the susceptibility will diverge. It's intuitive why the susceptibility is divergent, because it means the system wants to order. It's just there in the board of developing spontaneous order. So the slightest perturbation that says, hey guys, let's go there, they all want to go there, okay? So that's the meaning of the infinite susceptibility. It's this tiny bit of insinuation, let's do this, and everybody does it because they are almost want to do it spontaneously, okay? So that's the critical point, just the border, the onset of order, okay? It's less trivial, but we also know in that kind of system that the way the susceptibility behaves is that it will diverge as a power law in the order parameter, control parameter. In this case, it's the density or the interparticle distance, can be the temperature. So there's a critical value of the order parameter, and the difference from the order parameter to the minus gamma, that's how susceptibility diverges in a second order transition. Gamma depends on the system, okay? So it's a so-called critical exponent. It can depend on the model. So if you look at this, you can say, oh, okay, maybe, so this is very similar to what another disorder transition is doing. So can it be that these swarms, these insects that look simply disorder, are actually very near a critical point, are actually on the verge of becoming ordered? This is also another evidence that keeps you pointing in that direction. Is look at this, the left column here, then we go back to the right column. But the left column, you see, this is the experiments. This is the Vic-Shake model. The Vic-Shake model near when you put the Vic-Shake model at the critical point. So we know what the critical point is in the Vic-Shake model, and you do different sizes. So you see that the susceptibility increases with the power law, just like the swarms appear to be doing. Okay. So again, this looks like a critical point. So we will explore this, but so to explore this, let me remind you what we know in equilibrium statistical mechanics about these critical points. So basically, there's two things we need to know. So first is that, as I say, we know there are power law divergences like this one. So the susceptibility will diverge as a power law with some exponent. But since the susceptibility is connected to the fluctuations, and we can do this in the exercise sessions, it's not too hard to arrive at this relation. The susceptibility is related to the integral of the correlation function, okay, which in turn is proportional to the variance of the fluctuations, okay? But if key is divergent, then it means that the correlation length must also be divergent. Because remember, the correlation length is describing the exponential decay rate. If I do the integral of the correlation function, and the correlation function is an exponential, it will be convergent, it will be finite. So if this, for the integral to be divergent, the function must not be an exponential. It has to be to decay slower than an exponential. And this means that the correlation length is infinite, okay? It will be useful for what follows to rewrite. So rewrite invert. So the correlation length diverges. So we introduce a new exponent, different exponent to describe that divergence. And if you invert this, you can see that the correlation, so the susceptibility will also diverge as a power of the correlation length. Okay, both things they diverge. What does the correlation function do near a second order transition? Well, it turns out that you can show that you can write it in this way, where you have a power law times a function of R divided by C. So that function f for large values of the arguments will be like an exponential, okay? When, so this f is decays fastly, decays like an exponential. When you go, this is when you are near the critical point. When you are exactly at the critical point where the correlation length is infinite, then what happens is that the f is just going to some value. It's not contributing any trend, and what's left is just the power law decay. So correlations, when I started studying this, I was a bit confused, but when the correlation length is infinite, it does not mean that correlations do not decay. Correlations do decay, only that they decay slowly, like a power law, giving you a divergent integral for the correlation functions, okay? But they still decay. And the way they decay is, it's called this scale-free form. Okay, so just to give an example, this is a so-called scaling plot, okay? So this is the Ising model. There's just simulations of the Ising model, but you see if you plot, instead of just the correlation function, you multiply it by the some power of the correlation length, and here you use this rescale variable, then you get that all correlation functions at different temperatures, at different correlation lengths, just collapse and fall on the same curve, okay? And when you are at the correlation, at the transition, when the correlation length is infinite, you have a power law. And this is just to show what's the idea of the scale-free correlation. So the yellow and the blue curves here, this and this, these are just exponentials with the same scale. And here what I'm doing is I'm plotting I choose some scale, R0, and here I renormalize the function by its value at R0, okay? And as you can see, the exponential has an intrinsic scale because when I do this plot, the function, the exponential looks different. The decay looks different, right? So here I use R0, 1, and 100 and say, in one case, the decay is low, and in the other case, the decay appears to be fast, okay? But when you do that with the power law, they still look the same. They fall on top of each other. So they don't have an intrinsic scale. The scale is the scale I am imposing, which is R0. Okay, that's the idea of scale-free correlations. Okay, I can choose the scale. So we're going to try to apply these to midges, but we must remember that these results will have to be corrected by the fact that the systems are small, they are finite. Okay, so all that I said is okay, but applies strictly in the thermodynamic limit. When the systems are small, we have to make some corrections, and so these corrections, when you study the experiments in condensed matter, practically do not matter much. It's difficult to observe the finite size effects in condensed matter experiments. But when in the 70s, when this issue was started to be studied heavily through numerical simulations, obviously simulations are small, and so it was developed this machinery of finite size scaling and finite size correction was developed, and it turned to be very useful because you can actually use finite size to infer results about the thermodynamic limit. In particular, you can use finite size scaling to compute critical exponents. Okay, so and in our case, we can use it for the experiment, which is an experiment with a small system. Okay, so the idea is that if your system is finite, nothing can be divergent. So the infinite susceptibility of the thermodynamic limit is a reflection of the fact that the susceptibility is growing with the size, as a certain power of the size went to infinity, so you have an infinite result. But see, if the system is finite, nothing can diverge. So instead of saying the power law, for instance, for the susceptibility, you replace it by that scaling law, where you have a power of the correlation length multiplied by some function of a dimensional, non-dimensional variable, which is L over, so L is the system size, linear size, divided by Xi. Note that in all these scaling relations, since you are looking at functions which you don't specify, like this f, I don't know what the function is. I'm only saying that it's a function of L over Xi. So I can rewrite things, and I can put L as a power there. So I just multiply and divide by L to the gamma over nu, okay? Redefine the f, and I can get a seemingly different scaling form. It's actually the same scaling form. But it's more useful to have L instead of Xi, right? Because I know what L is in my system. It's easier to measure than to measure Xi, okay? And you don't know what the function is, but you know what it must do. So what you know is that, so I'm writing that, so chi is L to the gamma over nu times this G, I write it, okay, over Xi. So what I want is that when L is very large, so if L is much larger than the correlation length, then the susceptibility is ruled by the correlation length. So I'm saying that if when x is goes to infinity, okay, so G must be just x to the minus gamma over nu. Okay, so then for when L is very large, then the prefactor gets cancelled, and I get the correlation function. Okay, which will dominate the. But in the opposite limit, this will be a constant, and it's the length that dominates how the susceptibility is behaving. Okay. And so many results, and I will use this soon. So this is the idea. The idea is that the new variable I'm going to introduce is the ratio between the correlation function, the length, and the system size. But the system size, this function can be rewritten this way, because so I use the fact that the correlation length is a function of the control parameter, right? The temperature, or in our case, would be the nearest neighbor distance, and so you rewrite things, and this L over Xi becomes this expression, okay? Becomes this, and this is the so-called scaling variable, okay? And that will turn out to be important in what follows. So this is an example. This is not experiment. These are simulations of the Vixek model. But this is a nice plot because it illustrates how finite size scaling works. So you have some susceptibility that you expect to diverge in the thermodynamic limit, but the systems are finite. So what you find is that the susceptibility peaks, and it gives you a peak whose height grows with system size, okay? And so you can, here, oh, sorry. Okay, so here, this variable is just the control parameter, okay? It has some critical point. Here, you have the same plot with the scaling. This is the scaling plot, okay? So this is the scaling variable, and this is x. Okay, here they used n instead of L, but in this cubic system is the same. It's just a 3 that appears there, okay, just as a cube root. But you see that this near the critical point, this is actually, you can actually get a good collapse, okay? So what happens with the susceptibility when the size grows, okay? So we are used to thinking about this. We have a system, we change the control parameter, and we watch it, the susceptibility diverge, or the correlation length diverge. But when you're looking at experiments, we cannot control we don't have access to the control parameter. Well, we have access, but we can measure it, but we cannot manipulate it. So it's the midges that decide what the interparticle distance will be. I cannot change that, okay? So we have to look the susceptibility as a function of size. And it depends on what you're fixing, what you will get. So if you fix x, so you have something like it's this. You're following this curve here, and you see that if you're fixing x and you're not exactly at the critical point, then the susceptibility will saturate. Okay, and that's what happens here in this curve. Okay, I'm coming back to this later, but so saturate. If you fix x at exactly the critical point, then the susceptibility will diverge. But rather than looking at it that way, it's better to think that we are fixing y, okay? So if you fix y, so here we are plotting, we're saying the susceptibility is this power times g of y. So clearly, if y is fixed, if I fix y, then I will see that the susceptibility diverges as a power of the system size. But there are basically two ways of fixing. Well, there's one way. It's just to have it fixed. But it's clearly, so if you say x, if you put x equal to x critical, then you trivially have a fixed y because you have y equal to 0. Yeah, okay. And in principle, you could do that, but you don't know what the value, this also happens in simulation. So apart from a few cases, like the two-dimensional Ising model, you don't know what the critical value of your parameter is, okay? But what you do know is you can fix, for instance, you can choose some y star. So imagine that what you can measure is the maximum, okay? So you can get a y star that will give you the maximum susceptibility, because you can go through the curve, okay, and you see what's the maximum. So when you fix y star, so if y star is fixed, so this is y star, this is sorry, let me see, it was L to the minus, okay, it's L to the minus 1 over nu times x minus. Okay, so that defines some x star which depends on L, which is kind of an effective critical value. Okay, and so you can follow the susceptibility at a fixed y, which means changing x to be at or very near the maximum. Okay, this we call surfing because you go at the top of the wave. Okay, so if you do that, that's another way to fix y, and that means following the black curve in the figure. Or if you don't fix it exactly at the maximum, you fix it a little bit off, and follow the other curve. And as you will see, if you do that, then you get a susceptibility that grows with the system size. Okay. So the correlation functions, in turn, yes, sorry.
So maybe I missed something, but in the previous figure, in graph A, shouldn't all the peaks in susceptibility be at the critical value of x?
Oh, no. Oh, that's a good question, but it's not like that. The peaks are just at the maximum of the scaling function g. And this maximum, there's no reason why it should be at y equal to 0, right? So that's why what happens is that you have an effectively, if you just measure the critical temperature or the critical density, it actually depends on size. I mean, it depends on how you define it. If you define the critical point as the maximum of the susceptibility, you find that it depends on size. And then you can work it out. You can invert it here. So this x star, okay, x star will be the actual infinite length, infinite size critical point plus some correction, okay. So sorry, this should be here. It should be like this, okay. I think I just messed up with the sign because, so this should be like this. So there's a finite size correction. When the L goes to infinity, then the critical point is the critical point. But if you are looking at finite systems, then, and also you can look at different quantities. You can do the susceptibility. You can look at the specific heat, and there's no reason why they should have the maximum exactly at the same place. Okay.
Okay. Thank you.
Okay. So, where was? Okay. So this is just to point out that also the scaling law we wrote for the correlation function has to be modified when the system is finite, and basically it means that you have to use another variable here, so you must include also this ratio of the system size and correlation length in the scaling law, okay? So you have a scaling law that's valid when the size is much larger than the correlation length, and another scaling law that's valid in the opposite case. They look the same, but they are different because in principle the functions f and g are different, okay? But they look the same. So in our case, the case we are interested in is when the correlation length is divergent. And so in that case, basically, you can just forget about the second variable and write the same scaling law, apparently the same scaling law we had before, but instead of using the actual correlation length, which is infinite, we use the system size. So in this sense, the system is scale-free, but the system, the size, will act as a scale, as a correlation length, okay? So the system is scale-free in the sense that is no, that I can set the scale by changing the system size, okay? That's the meaning. It doesn't mean that the decay is a pure power law, as it would be in the infinite size. It's not, because there's a scaling function here. So when R gets, of the order of comparable to the system size, it will no longer be a power law, okay? But it's still scale-free in this sense, in the sense that the scale, correlation scale, is the system size, okay? And this is important because if we go back to the correlation plots, then you could say, okay, but these correlation functions do not look at all like power laws, okay? Okay, and that's true, but it does not mean that they are not scale-free. In fact, what I will argue is that they are scale-free, because the scale, in this case, we can characterize the scale for when you are near critical, you can characterize the system with the crossing of the zero. That will depend on system size, as I will show, okay? So, okay, final effect. So, when you can work out. So when you have this new scaling law, and so what you can show is that if you compute the correlation function using space average, which, as I said yesterday, implies that you will have a zero. So if you do that, then you can show that that zero will behave in either of these two ways, depending on whether you are in a scale-free situation, that is at a critical point or not. Okay? And so, if you are at a situation where the size is, I think I put it the other way around. No, okay. So if the size is larger than the correlation length, okay, so the correlation length is small, when you compute the correlation functions at different size, you will see that the R0 grows, always grows, but it grows logarithmically with L. So this is the reason why R0 is not a correlation length. Okay, it has a different trend. Okay, and this is what happened in this case. This plot. So this plot, sorry, this plot here is precisely that. So see, this is wrong. This is actually R0. Okay, this is R0 as a function of the system size, and you can see that this is not quite saturated. So it looks like it's saturated, and actually this will continue to grow slowly logarithmically because this path is this one. Okay, so we're not following the system to criticality. We just start more or less near what could be a transition, but then we stay far away from the actual transition. Okay, but that's not what midges do. Okay, and that's the whole point of this discussion. So in the other case, if you are in a situation where the correlation length is much bigger, much larger than your system, then what you see is that this R0 grows proportionate to L. Okay? And so back to midges, this is exactly what happens with midges. So all of the phenomenology described for finite system size is what we find, what you find. So you have a midge swarm, we have digitalized, and we compute the correlation functions, okay? And then we look at the susceptibility as a function of size. This I showed you before. It grows with n, okay? You look, so the top row is the midges, is the experiment. The bottom row is the simulation of a Vic model, okay? So you have that, again, this is R0 rather than psi. This R0 grows linearly with system size. So that means that you are near the critical point. So you are at the critical point, or you're doing the surfing and following the maximum or very near the maximum, okay? And finally, you can measure the actual value of the control parameter that the midges are using. And you see, and I find this very compelling, you see that this parameter is changing with size and is kind of being tuned as if the midges knew what we mean by surfing, okay? Because they're doing exactly that. So this is a log-log plot, and it grows. This is what you have to do by hand with a Vic model to get a key, a susceptibility that grows as a power law. Okay, so midges seem to be choosing the mutual distance, interparticle distance, in such a way as to always stay at some fixed value of the scaling variable. Actually, probably if they are doing something like that, what they're doing is they're choosing to be near a maximum of a susceptibility or something like that, something that's meaningful for the functioning of the swarm. Okay, but I find it quite impressive that they're doing this. So the conclusion of this part is that while swarms behave like you expect from a Vic model that's just tuned very near to criticality. And this tuning, important part is that to tune the model near criticality, you're not hardwiring into the midges genome the value of the control parameter, because you have to change it when the size of the swarm changes. So somehow there's a mechanism that leads these insects to choose the parameter that maximizes or nearly maximizes the susceptibility, and that's why they're critical. Okay. So there has been some discussion. Other groups did not find the same results. The difference was that these are wild swarms, while the other groups measured sums in the laboratory, and this can disrupt a lot of things. So there were some exchange of ideas, and people say, no, you're actually measuring, you're mostly measuring turbulence. This is too much influenced by the wind and by the current. But if that were so, it would be very hard to explain how, I mean, why, if this is an effect of just turbulence and external conditions, why would these guys tune their control parameter that way? Okay, so this is maybe not completely closed, this discussion, but I find that this mechanism of tuning, if you look at all the variables that are changing, not just the correlation, the susceptibility, but everything that's happening is pointing to a direction where there's some mechanism or some reason why midges want to be critical or near critical. Okay? Yeah.
Do you have an idea what would be the evolutionary benefit of staying near critical value?
Not really. What has been speculated is that these groups want to be highly responsive to something, which could be to predators, or I don't know, this as I said, these are mating swarms. Maybe this makes the system more, better for the mating purpose. So I don't actually know, but the idea is that a good high response is good for some reason. So maybe it's clearer for flocks, birds that have against predators. Here, it's not quite clear. But yeah, that's still open to speculation. But it's a fact that in biology, you can find in biology many instances where systems are very close to a transition, right? So biological criticality has been discussed quite a bit, and this is another example of that. But I don't have a clear explanation. That one supposes that it has to be some evolutionary reason why these guys behave this way, but I don't know about that.
And how does this relate to self-organized criticality?
Well, I don't know. You could say it is self-organized if you assume, because you would have to assume some regulation mechanism, some tuning. But I don't know, self-organized criticality is a term that usually applied to different system models, very out of equilibrium, with a clear input of energy. So here, okay, this input of energy, because this is active matter, but the setting seems to be not quite the same. But yeah, eventually, I guess you could call it self-organized in some sense. Yeah. Okay, so this is the first part. I hope I have been clear here and that you could follow this reasoning and these arguments. And the conclusion is that the Vic model is quite successful in explaining the near criticality of not why they are at criticality, but once you accept that, a near critical Vic model explains so far these observations. But you can do more. You can do better, or from the same observation, from the trajectory, you can extract more information, and you can extract some information about the dynamics. Okay, and when you start studying dynamics, then the Vic, you will find that the Vic model is not enough. Okay, when dynamic coming. So Let's see what we will measure, what I mean by dynamics, and there are different things you can do, but at this level, and what has been done with images is studying the time correlation functions, or actually space-time correlation functions. We yesterday defined these correlations. We looked at some examples. Now the question is, how do space-time correlation functions look when the system is near critical? Since we already know that about midges, we are preparing ourselves to study what we expect will be critical time correlation functions. Okay, so let's see what the theory in condensed matter tells us about these functions. And well, this is quite a subject, but trying to keep it to the minimum, what is known, this is something that was developed during the 70s. The big names here are Halperin, Hohenberg, and Wilson. And there's a quite famous review article by Hohenberg, and about this dynamic, I said Hasenberg, it's Halperin, sorry. Hohenberg and Halperin, this quite famous review in Reviews of Modern Physics in the 70s, 1977, I think, which gives the theory of the dynamic critical phenomena. So, but condensing that to the bare minimum, what is known is that this correlation function, okay, which is where I have transformed, done a Fourier transform on the space part, but I have left the time part as it is. You can also do a Fourier transform on time, but we will work with wave number and time. Okay. So it has a scaling form. So it can be written in this way here. Okay. So this is the static correlation function. So just the correlation function evaluated t equals 0. And the time dependence is described by a scaling function of this form, where essentially you have this time divided by the correlation time, where the correlation time is the spectral correlation time. I will write it again, but we defined it yesterday. And there's a shape. So this is a time scale, but the shape of the decay depends also on k, and actually depends on the product of k times psi. And this is how. So there's also a scaling law for how the correlation time evolves with the as you change the observation scale, which is just the wave number. Okay, and it behaves this way. So the thing is, this looks quite complicated, and it more or less is. But the point is that if you can fix, so if you change the observation scale in such a way as this product is constant, then you have correlation functions that decay with the same shape, okay, always the same shape. And the only thing that changes is the correlation time. And how it changes? Well, it changes as a power of the wave number, okay? That power is called the dynamic exponent. The z is a dynamic exponent, and again, it depends on can depend on the kind of model you're using, okay? It's a universal exponent. I mean, it depends on the qualitative details of the model. It does not depend on the values of the coupling constant, for instance. Yeah? But there are several known values that this exponent can take. So, and the point is that, and this function, this omega is finite for when x goes to infinity. So you can show, okay. So yeah, I needed to show you this. So what you can show is that, so you have, when you go to k equal to 0, so you study the relaxation time of the global quantity of the, say, the whole polarization, okay? Then what you have is simply that the relaxation time for the global mode is proportional to a power of the correlation law, or if you are finite size, a power of the system size, okay? So this is an example for the Ising model. And here I'm just plotting correlation time as a function of the correlation length. And you can see that when you go near, so when this starts to grow, which means you are going near the critical point, then you have a power law where the correlation time grows with the correlation length. So if you think of it, it's not strange that the correlation time grows with the correlation length, because somehow information must be propagated, okay? So what's the correlation time? It's telling you how the system forgets about itself, how the system forgets about, so you have a pattern, this pattern evolves, and it's losing correlations. But you can't just, randomly change the pattern all over to make it forget, because you have to do it, you have to lose correlation, but you have to lose correlation in a way that preserves the static correlations. Okay, so the space correlations have some shape. And if these space correlations are long-ranged, then you can see that you have to change the system as you evolve in a way that has to preserve this. So you have to change it in a way that preserves the long-range correlation. So you have to coordinate somehow how you decorrelate in time. Okay, so there must be some kind of information exchange or flow so that this thing can happen in a stationary way. Okay, so the longer the correlation length, the larger the correlation time. What's not trivial to see is that that relation would be a power law. Okay, but it is. Okay, you can work it out. You can do renormalization group arguments. You can do stuff, and you conclude that it's a power law. Okay. So we are going to test this, and we're going to do it with finite systems, as I argued there. And so we are basically looking into this. So we'll be trying to verify that when we normalize the correlation function, then everything is a function of just k to some exponent times the time. And then we will compute also this time and plot the time against the system size, since we know the system size is essentially the correlation length. Okay, so the correlation length is fixed, it's infinite or almost. And so we expect that if this is true, then the correlation time should grow as some power of the system size. Okay. So again, to summarize, we were computing this correlation function. This is the time correlation function at a fixed wave vector for the velocities. And this is following the definitions I gave yesterday, only that here I have integrated over all the angles, because we are assuming that our system is isotropic. And so again, this is something we do to get improved statistics. So we can use, all the pairs lying at a given distance, in a given shell. And so we do that integration of the angles, and that's what you get when you integrate. So this sign comes from integrated an exponential that appears because you have done a Fourier transform. Okay. And we compute. This is, I remind you, this is the definition for the correlation time. Okay, this tau, which we expect that it can depend on k. In principle, the shape of the decay will depend on the wave number, but we have the scaling law, and we know that we will be setting this will be fixed. So we expect that if we fixed this k times c, in our case, will mean fixing the product k times L. So if we change k as we change the same system size, then we expect that the shape of the decay will be the same. And in fact, somewhat surprisingly, that's what happens. So the first plot is just the correlation function for different wave numbers for single swarm. And then we compute the correlation time, and then you try to rescale with the correlation time. And you see, if you just do for one swarm, it doesn't work because as we change different Ks, the shape of the decay changes. It also is not working very well for different swarms at the same K. But if you change both the swarm, that is the size, and K, then you get a much better collapse, which is this one, okay? So this seems to be working. What now we need to check whether this can be done with an exponent, with the K to the Z. And in fact, it can be done, okay? So the top row is the natural, it's the experiment, it's the swarm. The bottom row is the Viksik model, okay? So again, Viksik model obeys this dynamical scaling, okay? So this is good. Both systems seem to be, so Viksik, we have tuned it by hand to be at the critical point. The midges seem to obey that. It's interesting that the correlation length that we are measuring in the experimental system is actually, it's relevant in the dynamical sense because it's also ruling the correlation time. So we're looking at something that's, so this correlation length is giving an important information, it's capturing important information about the system and about, not only about its static structure, but also about the dynamics, okay? So that's, I think that's an important point. But now I will show you the actual values of the exponents of zeta, z, and I will show you they are different. So the Viksik model is actually not okay to fully explain what the swarms are doing because it cannot explain the dynamical part. Okay, so this is experiment. So this is the fit of the relaxation time against correlation time against correlation length. And the exponent is around 1.4, a little bit below 1.4, 1.35, 0.37, okay? If you have ever looked into the literature of dynamical critical dynamics and have looked at that, then you notice that that exponent is very low. So if you just do Monte Carlo with the Ising model, that's called model A in this jargon, which is a relaxational model, which is basically a Langevin equation overdamped without inertia, then you get around 2, a value around 2. If you add conservation of the order parameter to that, you get an even larger value. You get a value around 4, okay? If you put inertia, there are equilibrium inertial models. One of them is called model G, which was invented to describe antiferromagnets. Then the value goes down, but not enough. It goes down to 1.5, okay? So this is quite a low exponent. And the interpretation is that information is traveling quite fast, okay? Not ballistically, okay, which would be roughly zeta equal 1, so not with constant speed, but quite fast, faster than diffusion, which gives you zeta equals 2, okay? So, and when you do this with the Viksik model, you get an exponent which depends on the activity. So if you do Viksik model with very low activity, meaning low speed, low V naught, you get a critical exponent that's around 2, that looks like, model A, just Ising model on the lattice, okay? Actually, if the model is active, so there's a crossover to a lower value of exponent. So activity is a mechanism that can lower the critical exponent, which looks more or less reasonable if you think what's happening is that activity is improving communication, is improving the information flow because it's actually, physically transporting particles which carry information. So information is not carried only by the interactions, by, giving, sorry, have a question? Okay. But it's not carried only by the interactions, but it's also carried by physically, like a convection. It's a sort of convection. physically moving the particles. Yes?
Well, but from a universality class perspective, shouldn't we expect this exponent to be the same for the same model?
Okay. Yes, but you do have, models have different regimes, okay? So if you are familiar with it, you can think of it in terms of fixed points of the renormalization group. So what happens is that activity, so when if the model is not moving, if you have V naught exactly equal to 0, you have 2, okay? If it's moving, but you can actually look, if it's moving, it should go to the other fixed point, which is 1.7. But it depends on how far or how near you start from those fixed points, how large your system has to be, and how close you have to be to the critical point to actually observe them. Okay, so when you do a renormalization group, it's you know that the fixed points will give you the values of the critical exponents, but that can be used directly only on the thermodynamic limit. If you look at finite systems, you have these crossover problems. Okay, so you have in this case you have an exponent that starts at 2 and goes over to 1.7 at huge system sizes. Where, by the way, this starts to fail because this is a fixing model, and at huge system sizes, then you have to worry about whether it's actually second order or not. Okay, you have to enforce incompressibility. Okay, so in simulation, it's very hard to see that as a function of size. But what you can do is you can start nearer to the fixed point, so you increase activity, and then you see the other exponents. Okay, but it's a good question because this is a big issue. When we studied the things at university, usually finite size is kind of left aside, but these phenomena, this crossover phenomena, which are very tight linked to finite size, are essential to grasp, to understand, and to apply to biological systems which are finite. Okay, so okay, so my point was, so this is not enough to get the experimental result, but it's true that activity will lower the critical exponent, as did inertia. Okay, so there's something missing here, and you can intuitively, you could guess, okay, so we know in equilibrium, dissipative systems, when you add inertia, you got lower critical exponent. When you add activity, you get a lower critical exponent. What if we add the two things together? Can we get something still lower than 1.5? Okay. Well, the short answer is yes. The path to that answer is quite long. I don't have time to do it here. But yes, if you add inertia and activity, you can get an exponent that's close to 1.35. I will show you a simulation that does that. Let me briefly show you the model that you need to do to add inertia to the fixing model. This is called the inertial spin model. And the idea is, let's go back. So if you look at this, so this is a way that you can write the fixing model in continuous time. So you write just a Langevin equation for the velocity, and you say, okay, I add an interaction that's ferromagnetic, okay, in the velocities. Now, to go to the inertial spin model, we will add another variable. We will add the momentum, okay, or the spin. So, and we will try to, what we do is a theory like we learned in classical mechanics, where you have canonical conjugates of the position, you have a momentum. Here, we invent a variable that's a canonical conjugate of the velocity. So it turns out that the relevant value is a variable. It's related to, not exactly the canonical, but related to the spin, which is as instead of the analogy is instead of using the linear momentum, I will be using angular momentum. Okay, and since the modulus of the speed is fixed, then it's better to use angular momentum. But it's an angular momentum which is internal to the particle, so it's actually the spin. So the spin what the spin does is to generate the internal rotations of the particles. So the velocity, each particle rotates its velocity around itself. Okay, so that's the definition of spin, the generator of the internal rotations. And so you add the spin in the simplest way possible here, just like, simple kinetic energy, no interaction, nothing, just kinetic energy. And you then write the canonical equations, which are these, okay? Which look a little bit weird. You have those vector products. And the reason is that we are not using position and momentum, but you're using position and angular momentum, okay? So velocity and spin. And you have to work it out, but it comes out easily from the definitions that those are the actual canonical equations, the Hamilton equations, for this Hamiltonian here, okay? Where Hamiltonian is, of course, in quotes, because there's an x equation which is x dot, the derivative of the position is equal to the velocity. And so when you put the three equations together, then this is no longer a Hamiltonian system, but that was the inspiration. And so simply what you have is that you have a dynamical system where the spin is telling the local velocity to rotate, and the way the spin is changing is according to the interactions, okay, which are the same here. Okay, and this part is just the noise you need to have some temperature, to have some fluctuations, okay? So as I say, it's a long way to do it. You can do some calculations, you can do some field theory to try to add evidence for that. But the simulations, this is the simulation for the model I just showed, and they are quite compatible with the critical exponent that's around 1.35. Okay, so that's our current understanding that for this kind of systems, so if you do not worry about the dynamics, then the description you get from the Vicek model is okay. But if you want to understand the dynamics, you need to add inertia, and you need to study this kind of system, these kind of models which are more complicated because there's another variable, and they are active, and so they're more complicated to study. But they actually seem to be needed when dynamics is concerned, because inertia is a player here. And also, I didn't have time to show that, but it's also a player in flux, in bird flux. So the propagation of the order parameter I showed, to explain that, to get those waves, you also need some inertia, okay? And you also need this kind of model, okay? Okay, so I hope I've been clear with that. So I have a few minutes, and I would like to conclude with some more philosophical speech, which is why, just a little bit to tease you into thinking about why we can do this. I mean, why we can apply statistical physics to biology. And exaggerating a bit, I would say biological physics is statistical biological physics. Okay, in some cases it's not true, of course, but in general, I think it's quite true in many cases, because if you look at all these examples here, which are different scales and different phenomena, what you see that the phenomena here have in common is that there's a collective mechanism going, operating. So you can do some abstraction and forget about the small things, but typically the result, the biological function, is the result of many units interacting and doing something, okay, at different scales. So in our case, it was many midges doing something. If you go inside the midge, you will have many cells doing something. If you go inside the cells, you will have many proteins doing something. But the molecular part is almost always, I'd say, present in biology. And so that's the reason why you can do statistical physics. There's an interesting, I will quote William Bialek, in one of his classes, you can find in YouTube, he says the following, which is interesting. He says, the way we teach statistical mechanics in the university in the physics courses is the same. It's more or less the same. So we first teach mechanics, classical mechanics. We then teach electromagnetism, then we teach quantum mechanics, and then we teach statistical mechanics. And this gives the impression that statistical mechanics works because we know the dynamical rules, because we got the microscopy right. But this is not the case. Statistical mechanics can work even if you don't know the actual microscopic rules. Even if you get them wrong, you can get good results. So in many cases, microscopy is irrelevant. You can get a good understanding of the brain without the right model of the neurons, okay? Of course, it depends on what you want to do, but if you're interested in studying memory retrieval and brain function, well, you don't need to know about the details of how the firing of the neuron works. You don't need to know about neurochemicals. So what you need to know is that the neuron is something that will get an input, and if this input goes over some threshold, it will just fire. Okay, and if you do that, you can get many things right. Okay, and so you can imagine that you can build a brain with neurons, but you can also build it with transistors or with some other stuff. Okay, this is the same as when you're studying, a gas. You don't need the details of how the molecules work, how they're done. You have electrons and you have protons inside. You can do thermodynamics and you can work out the law of ideal gases without going to microscopy. Okay. Of course, at some point, if you decide to put electricity and make a spark, just a spark across the gas, and you see the spectrum, and you start wondering about the spectral content, then you do need the microscopy, because now you're looking at something else. You're looking at a phenomenon that's not collective, but just microscopic. And to understand that, you need to understand the structure of the electrons and the electron structure of the molecules. And if you try to understand why a certain drug will affect the brain function in some way, then you have to understand that there are neurotransmitters and how neurons communicate among each other and so on. Okay, so it depends on what you do and what scale you're looking. But for many problems, you don't need to go into the microscopic details, and that's the reason we can make some progress. I like to picture this like Linnaeus, facing Boltzmann, in the sense that Linnaeus is the guy that did this classification, right? So looking into the details, working out the details, separating insects from mammals, and so looking into the details of things. Whereas Boltzmann, or maybe I should have put, Wilson, just the opposite. Just let's try to forget about the difference. Let's see what's in common, okay? So that leads to comments. So abstraction. The first thing is abstraction is good and it's needed. I guess you already know that. We need to do abstractions. We need to forget things, okay? We need to forget. So if you want to read a short story, you can read Borges, you can read, about abstraction, about why you need to forget, okay? That's Funes, you can read that. Also, there's this very nice book by David Foster Wallace. So he's not for fiction works, but he had a degree in philosophical logic or something, and he wrote a book which is called Everything and More, which is the history of infinity, of mathematical infinity. It is a very nice book. But among other things, he points out that around the Renaissance, so mathematics, in the Greeks' times, it was mostly geometry. Then it turned out to be a little bit more about arithmetic. And around the Renaissance, it started to go abstract, way abstract, to functions and spaces, abstract spaces and so on. And he says, what is maybe not intuitive, but the fact that the mathematics went to such abstract path actually made it more useful for applications, not less useful, as you might naively think. Okay, it was turned more useful. So we need abstraction to do science. And the other comment is about this kind of organization of things, of science, if you wish, of the way we think about things in levels about the different scales. An interesting read is this paper by Anderson, by Phil Anderson in the 70s, which more is different, which points out to this. So more is different means that at some point the things get so complex that there's a qualitative change in the things the system can do. And this goes hand in hand with changing the science, the scientific disciplines you use. So for very small things, you use physics. For a bit larger things, you have to do chemistry, and then you go to do biology and to do sociology, etc. And he argues that there's kind of a symmetry breaking in between levels, and this qualitative change actually justifies the fact that we have different scientific disciplines, because complexity, so when you have more things, you have different things, meaning you have new laws or new phenomena you have to look at that can be explained in terms of what's below. I mean, he's not denying that there's this sort of reductional you can do, but that they are qualitatively similar and that you need different concepts to understand them, okay? And so the final element here is Wilson and the renormalization group method, which is the way to formalize a little bit, at least to some point, these ideas. And it's the way we have to understand we can understand why the microscopic doesn't matter in the description of many macroscopic phenomena, okay? So I will finish with this quote, which I will read to you, which basically summarizes this way, this idea, which says, so nature is organized by scale. So there's an order to the universe we live in. Roughly speaking, little things affect big things, but not the other way around, okay? So particle physics underlies nuclear and atomic physics. Atomic physics underlies condensed matter physics and chemistry, and so up the chain. It's true that it can be difficult, it is very difficult, to make the leap, to jump from one level to the next. And new creative ideas are needed at each step. But this doesn't change the fact that there is an ordering, okay? Big things don't affect little things. And this is the reason why there are no astrology departments in universities. But there is another aspect to the story, which is not often stressed. Little things affect big things, but they rarely affect very big things. Instead, little things affect slightly bigger things, and this in turn affects slightly bigger things. As you go up the chain, you gradually lose information about came long before. Okay, that's the idea. The microphony is irrelevant. So a zoologist, interesting in the way that Starling flocks, has little reason to study the dynamics of the Higgs boson. This is also the reason science is possible in the first place, right? Newton or Einstein need not understand particle physics or quantum gravity to develop laws, write down theories that work extraordinarily well at large scales. The mathematical formalism in the 1970s was developed that makes these ideas concrete. This formalism is called the renormalization group and provides a framework to describe physics at different scales. It gets little coverage in popular science articles, yet I do agree with this. It is arguably the single most important advance in theoretical physics in the past 50 years. while zoologists may have little need to talk about particle physics, to talk to particle physicists, the right way to understand both the Higgs boson and the flocking of starlings is through the language of the randomization group, okay? And again, this is the reason why we can do statistical physics for biology. And with this, I thank you, and thank you for your attention, okay?
Thank you very much, Tomás, for this wonderful talk.
Thank you.
So there are questions over there.
Thanks, Thomas, for the very interesting talk. I'm very interested in this comment of yours and how, because like really in the interface between like working with ecology and physics, etc.
Mm-hmm.
So coming from a physics background, I've heard this story about how physics can be applied to other sciences and the tools that we have are sufficient in many, many cases. But facing and learning more and more about ecology, I learned about some details and some phenomenological aspects of ecology that did not fit into my current understanding of physics. That might be because I'm not very knowledgeable, but that also might be because like physics is not there yet. So I would like to ask you, which is much orders of magnitude more knowledgeable than I am, if you think that something like the existence of final cause in biology, for instance, behavior is determined by the need of an animal to get to something. That is a final cause. That is not an effective cause in which there is a force that applies to something. The animal wants to get somewhere, and then it navigates. So this kind of different aspects, do you think that the current tools that we have are sufficient, and it's just a matter of doing the really important and really large work? Or do you think there are breakthroughs that need to happen before we can actually use the entire tool and explain ecology, explain biology as such?
Okay, well, I think a little bit of both. I mean, we can use the tools we have, and I think I showed you at least one example where they work very well. But yeah, I'm not arguing that knowing physics is just enough to understand everything. In fact, that was not Anderson's point either. I mean, what I mean is that we can and we should use the tools of statistical physics to go to larger scales. But yes, there might be a point where at some larger scale, like in ecology, the complexity of the system allows things to happen that you didn't think before and that not quite fit into the laws you know, and then you have to develop something new. It doesn't mean that, so I don't know how to say it. So it doesn't mean they are emergent in the sense that they come from above, okay? It's not like animism, you know, because this word, so now that you ask the question, it's emergentism, okay? So in the early 20th century, there was a school of thought that was called emergentism that said, okay, like biology just does not come from below, from the physics and from the biochemistry. It's something that emerges. Now, the opposite of that is reductionism, okay? So Anderson viewed himself as a reductionist, but he's also being called a neo-emergentist in the sense that he says, yes, things are based on what's below, but that doesn't mean that something qualitative, that new ideas, new laws, or new kind of sciences is needed to explain what comes below. So these guys are called microphysicalists, in the sense that the reductionism would be, you start with quantum mechanics and you go all the way. So, but that's not what Anderson say, and so he's saying at some point things get too complicated and you must do some kind of phase transition. Okay, so the short answer is you should do both. At some point, yes, you can probably come up with things that just don't fit in the laws we know, and you have to work out new laws, and then you will have also to work out what's the connection between the new laws and the step below. And that's certainly going to be hard, but yeah, but that's the way to go in the end. Okay.
I have a question. Okay, you have one? You first.
I also wanted to go a bit in the same direction as the previous questions. I was wondering, what is your perception on, like, when people work on the same scale, but they have completely different views on the same topic? Like, sometimes you work on the scale of interaction between animals and from a physics perspective and from a biological perspective, and still you are not able to communicate with the other person by lack of language or lack of common interest, but actually the thing that you want to understand is like essentially the same. How this barrier should be crossed?
Yeah, I'm not sure, but I don't think that's a fundamental problem. I mean, this is probably a problem of culture and the way we were raised in different sciences, and especially like 50 years ago, scientific disciplines were more, much more separated than they are today. I think today we have a view where science is one big thing where you simply have to specialize because you cannot get everything in your head, but it's not. But it's just one piece of knowledge. But these backgrounds are there, and yeah, we're influenced by them, and it can get very difficult to talk to people who were raised with a different language. But I think this is a question of time. Eventually, these things will necessarily percolate because we are studying systems and we are talking to each other. It's difficult, but eventually the new generations will learn to integrate those aspects, I think, or I hope. But I think it will eventually happen because, because you realize that that's a good thing. So it's difficult to do, but eventually I think we as as a collective, we will manage to do. But it can be frustrating when you have to go to it, because probably because what's happening is that the tradition in biology is to look at the details, to try to get the details right and look at the differences. This animal is doing this, but this one is doing not quite the same, because whereas the tradition in physics is more like, okay, everything is a sphere and just go on, okay. So we have to learn to talk to each other, but yeah.
Yeah, over there. The biologists in the room can also comment.
Thank you, Professor Thomas, for your talk. I have a philosophical question, actually.
Okay, I'm not a philosopher, but
yeah. Because I started my studies in active matter in flock and behavior, like you presented to us. My thought about this field in the last years is this field achieved like a plateau in the discussions. And my question for you is, what do you think about the next years? What do you think will occur to this field, and which perspectives you have about the next year and the next years about the factorization fields? There's another problems we don't achieve yet. There's another question we don't answer yet. What do you think? This is my first question. So
yeah, okay. So I'll answer briefly to that. I really don't know, but there are some things you can do from the experimental point of view, I think, and I think they will be done. For instance, you can try to follow. First, you should try to get to study more species, because the data we have is for a few species. So we should do more. Like particularly, we should do experiments. In South America, have different animals. You should just try to look at them. So doing more experiments will show us how universal our theories are or not. And then the other things you can probably do is you can start perturbing, doing experiments with external fields, so with different kinds of perturbations. I think that's interesting because it will be, giving you a way to test whether the susceptibility, correlations and susceptibility go together, and they might give you an idea of why this criticality we observe could be if it's something. So the question is something that has to be there because of some physical law, or is something that is good for biology and that's the reason why it gets there? So I think that it's a question that's open. That said, I don't know. And then there's a lot of stuff I really don't know very well about collective behavior in microorganisms. Okay, our different systems have different problems. See, the medium is very important. So I don't know. There's probably interesting stuff coming from there as well. But in the end, I'm not sure. I've seen, fields develop. Typically, fields develop have like a burst. They grow a lot in a few years, and then they reach some steady state. And sometimes they're stuck there, and sometimes after a few years, a new breakthrough. Like I was doing glass physics in my postdoc, and sort of that happened. There was this big explosion with the spin glasses, Parisi, the theory, everyone doing that. It's a breakthrough. Then the thing stabilizes. Then we started understanding a little bit more structural glasses, correlation length, and that. Then another plateau reach. So I don't know. I understand your feeling, but we have to see.
Indeed, thank you. My second question is about your model, inertial Vijek model.
Yeah.
Yeah, just maybe you can show. Yeah. Yeah, this one. Okay, I got it. You give us a motivation to do this change in the model. And did you try to get some kind of how can I say Fokker-Planck equation from this model, or another mean fields equation to describe this kind of approach, or not yet? From these equations, can you get a Fokker-Planck equation directly?
I think so. What we have done is field theory related to that, which I can show to you. But there's a group of mathematicians in Korea that have done several variants of these things, and I'm thinking, I'm not aware that they have done specifically Fokker-Planck, but they might. You should check the literature about that. They might have done something in that direction. But we have done field theory in the lines of tolerant 2, something like that. So with Langevin equations, but field equations. Okay.
Thank you very much, Thomas.
You're welcome.
So I have more questions, but in the interest of time, I can ask you later. So let's thank Tomás again.
Okay. Are we doing exercises today?